Hi, this video we're going to talk a very important concept in thermodynamics. It's called the first law, the energy conservation. And here we're particularly looking at a closed system. A quick review, closed system versus open system. The difference is the closed system, there's no mass transfer. Open system, there's mass coming in or out. But both systems have the heat transfer or have your work transfer. In other words, there's energy transfer. Okay, so now let's talking about what constitute the energy. We heard about energy, this term a lot before, and we learned previously, about there's potential energy, P, and there's kinetic energy, KE. So let's quick review. What's potential energy? P is going to be mg, h is altitude. And kinetic energy is half mv squared, right? Okay, those are the basics. And think about it, if you are going to climb up a hill, and when you start from initial 1 to state 2, and what happens? Your potential energy increases because your height increases, right? And if you are going to reduce your speed while climbing uphill, and your kinetic energy decreases, because that's related to the speed velocity here. So that's energy. And that's pretty much energy used for mechanical system. But there are another type of energy that's in the thermodynamics is called internal energy. If it's internal energy, we have letter U, okay? So it's all other energy together. So now let's look at what are the internal energy. It's microscopic because it's related to the molecule. Internal energy of a system is the sum of all those forms of the microscopic energy. For example, here, sensible energy, it's the portion of the internal energy of a system associated with kinetic energy of the molecules. And latent energy is associated with phase. For example, from liquid to gas or from solid to liquid, that's different state of the system. When you go from solid to liquid, your latent energy should increase. Same thing from liquid to gas, your energy increases. And also there's chemical energy that's part of this internal energy. It is associated with atomic bond of a molecule. Nuclear energy, it's tremendous amount of energy associated with the strong bonds within the nucleus of atom. So if you cluster all of this together, that's going to be our internal energy. Then we just talking about those 3 different types of energy: potential energy, kinetic energy, and internal energy. Okay, now we're going to talking about a change of energy. Since it constitutes of the 3, so we're going to call change of energy is called delta E. E means energy. Delta means change, right? And then we're going to potentially have kinetic energy change. We could potentially have potential energy change, delta PE, and of course, change in internal energy. All those 3 will constitute the change of energy. Now, let's draw a diagram here. If this is my closed system, which is a rigid vessel, and it's closed system, which means M, my mass, is constant. There's no mass coming in or leaking out. And this is absolutely a closed system. So in this closed system, if there were energy change, if there were air inside, if there were energy change, what contribute the change? That's the next question we want to figure it out. What will result in, or what will contribute the change in energy? All right, so let's think about things. How about if I add heat to it, right? If I have like a candle burning at the bottom to add heat, to heat up the air inside, do you think the internal energy will increase? Yes, of course. So that contributes to change in the energy. And how about if I put this container in a frigid winter weather outside, and it's gonna transfer the heat from inside container to the outside, right? So that's the heat coming out. So that results internal energy decrease. So I could potentially have heat coming in or heat coming out. That contributes to energy change. And how about another thing? How about I add a work or the system does a work to the surrounding? That would change too. For example, I'm going to change this to, this is still a closed system and it has a piston here. And if I were trying to push this piston down, what happens? The air inside is going to be compressed. And so when you push the piston down, it's kind of like you're working out in the gym, right? You're doing the work to the system. What happened? The air compressed, the pressure go up, the temperature potentially go up. In that situation, your internal energy increases. So you have change your energy. So the work contribute the change in energy. And on the opposite scenario, you could have this air inside this piston cylinder expands by pushing this piston up. In other words, this system, the air here is doing the work to the surrounding, to pushing it up. So in that situation, just again, like when you go work out in the gym, you get tired, right? Your energy level gets lower afterwards. So what happened to when this air push this piston up? The air is doing the work to the surrounding. Your internal energy of the air will decrease. So in that situation, to answer this question, what contribute the energy change? Where do you have an answer? Could be heat, could be work for closed system, right? And now if we are thinking about for open system, which means mass can come in and out, coming out. In that situation, we have mass coming in or out. That contribute the energy change too. We have more mass, likely the energy increases. But now we only look at a closed system. So two means will be heat and work. So knowing that, we are going to write this very important equation. Delta E, this internal energy change, could be contributed from heat, and Q is heat. Could be contributed from work, that's W. Those two contribute the energy change. And here, I'm not going to use plus, I'm going to use minus. It doesn't really matter. We're going to define the sign convention right after this. But why they're using minus? Because throughout textbook, they're all using Q minus W in the textbook. That's what we're going to use here, just trying to be consistent. So delta E is equal to Q minus W. What that means, heat and work both contribute the change of the system. And now we are going to combine this first equation we have over here. Delta E is made of three terms: kinetic, potential, and internal energy. So if we were trying to expand that, we'll have delta U plus delta KE plus delta PE. That's equal to our delta U earlier we said. And that's contributed by heat and the transfer. So we have this equation as well. But now I'm going to assume things. In engineering field, we like to make assumptions. So assumptions we're going to make here is this system is stationary. If it's stationary, we know there's no speed change, which means kinetic energy is going to be 0. The change in kinetic energy is 0. And the same thing, there's no altitude change, so there's no height difference. So MGH, the potential energy change, will be 0. Then once we made this, we're going to be able to simplify this. So this will become 0 once we made the assumption. Then the new equation will be delta U, internal energy change, is contributed by the heat transfer and work. That's our internal energy change. That's our first law of thermo, right? Now, another important thing, like I said, this minus is kind of strange, and we have to have like a sign convention to define it. And so here is the last point of this video. We're going to talk about sign convention. On the left hand is if we were trying to use this equation, most general equation, we're going to use delta E equal to Q minus W. So energy change is contributed by heat and transfer. So imagine if I have heat coming into the system, if I have heat transfer into the system, would that make energy of the system go up? Of course, right? That's common sense and very intuitive. So Q will be greater than 0. When you have a greater value, delta E gonna be positive. So the change is positive, which means energy increases. Then intuitively, if there's a heat coming out of the system, leaking out of the system, of course that Q is gonna be considered as negative. That's gonna be our negative value. So that would decrease the energy. Now let's think about work. If there's work done by a system, so work done by a system will be this example. We just kind of demonstrated if you have a piston and this piston is being pushed up by the air inside the system. So that's work done by the system. Well, if the air is pushing the piston up, what do you think about the air energy? It's gonna decrease, right? So in that situation, my delta E should be negative to decrease. But I'm here having a minus value for W. So my W here will actually gonna be positive because I'm gonna minus a positive value to get a negative. So my energy will be decreased. Because work done by a system, then the energy will decrease. All right, so that is very important. Then we're going to looking at the opposite. If it's work done to a system or done on a system, work done to a system. So that would be example when the piston is being pushed down. So the air inside the system here is being compressed. So there's a work down to this air in the system. And you know, air compressed, the energy of the air will increase. To delta E to be increased, to be positive value. And here I'm going to be minus. So I'm going to be minus a negative value. So I'm actually plus a positive value to make my energy increase. All right, so that's a sign convention. Heat transfer is pretty intuitive. And one quick thing to remember about the work, since there's a minus here in this equation, in the first law of thermodynamics, we're going to consider about sign convention. We're going to use consistently in the rest of thermodynamics. Work done by a system, that's going to be positive. Work done to a system is going to be negative. Okay, that's all we have for this video. First law of thermodynamics. Delta E equal to Q minus W. And that is that critical since you're going to use a lot. All right, see you next time. Bye.